Okay, this is the Math 10 mock final page 4 solution. I misnumbered these. This is actually number 5, so threw everything off for the rest of it, but bear with me. So on this page, we're going to talk more about functions and inverse functions, and composite functions also. So here I have defined two new functions. One is k of x is equal to x minus 1, and the other is j of x equals negative 2 times x. One thing to remember about this function notation, I know that it looks like k is multiplied times x here and j is multiplied times x, but that is not what the function notation means. Function notation takes letters to represent relationships, and the reason why the x is in the parentheses here is just a way for the function to define how they refer to the input of each function, because a function basically takes a number that you give it and it modifies it and out comes a new number. You've done this your whole lives at EAC. You've used function machines, you've done input-output tables, and this is the real math version of input-output tables. So when you have k parentheses x, basically what you're saying is, hey, I got the relationship k, and I have an input called x, and I'm going to define the mapping or the function machine by using x as to represent the input. So when you have this, you could also write it as, hey, I have a relationship k. The relationship k has a box every time you want to plug the input into something, and the relationship is defined as box minus 1. And j is a function with an input box, and the way you define it is by doing negative 2 times box, for example. Okay? And you'll see why I refer to it this way. I think a lot of people have trouble with the fact that x looks like it's already filled in, and x is actually just saying, hey, you can put anything you want here, even something with x in it, which is really confusing. Okay? All right. So first what we're going to do is we're going to talk about the relationship that k and j are defining. So I want you to show 5 xy relationships for k of x using a mapping. And if you remember, a mapping diagram looks like this. It's got two blobs, circles, or ovals, and you're going to define relationships between a domain and a range, and the x's are going to be here, and the y's are going to be over here. And in our case, we can put whatever we want to. It says to define 5 relationships, so we could put whatever numbers we want over here in x. I could put negative 1, I could put 0, I could put 1, 2, 3. I've defined 5 numbers. Now I'm going to define where they go to in the range or the y area. So if I'm defining k of x, then basically k of x says, okay, I'm going to take the input and I'm going to subtract 1. So if I am going to find the mapping for x equals negative 1, it would be negative 1 minus 1, which would be negative 2, and so the new value would be negative 2, or the y value would be negative 2. Okay, so for an x value of negative 1, the k function defines a mapping from negative 1 to a y value of negative 2. So 0 would be, 0 minus 1 would be negative 1, so 0 maps to negative 1. 1 maps to 0, right? 2 maps to 1, and 3 maps to 2, right? This is obviously a function because not only is there only one y for each x, but like in this case, no x's are mapping to the same y, which is even more strict than a function. Because like remember, if it's a function, you can still, like if it's a function, I can have 4 map to 2 also. That's not a problem. 2 x's mapping to 1 y is not a problem. The problem is when one number in the x maps to 2 y's. That's a problem. Okay, then it's not a function anymore. All right. Let's do the same thing for the relationship defined by function j, which is multiplied by negative 2. This time we're going to do it using what we call a table. And so the table is something you've used many times in your life before, and it's very useful for trying to figure out what functions do when we look at it and we get scared and we don't know what it does. We just can go back to our primordial instincts with a function, which is to just plug in some numbers and see what comes out, okay? So our function this time is the minus 2 times minus 2 function. And so we're going to take whatever the input is, and we're going to multiply it times negative 2. And so negative 1 times negative 2 is positive 2. 0 times negative 2 is 0. 1 times negative 2 is negative 2. Negative 2 times 2 is negative 4. And negative 2 times 6 is negative 6. Okay? All right, so we've shown 5 xy relationships for j of x using a table. All right. Now, it says to find the inverse function of k and the inverse function of j. Now, we know that the k function is something minus 1. So the inverse k function, which undoes k, would obviously be something plus 1, right? So if we define the inverse k as something plus 1, the way we would normally write it in math is that, oh, x plus 1. What is x? X is the input. We define it as the input by putting an x right here in the parentheses. Okay? And so the opposite of the k function, which is subtracting 1, is the inverse k function. And the way we show inverse k is we put the negative 1 in the exponent here, although it's not an exponent, it's just a notation that says inverse, okay? Then it's defined as x plus 1. And the inverse j function, the j function, remember, is to multiply by negative 2, so the inverse j function would be to divide by negative 2, right? Because like multiplying by negative 2, the opposite would be dividing by negative 2. So you could write that like that or like this, okay? All right, you could also write negative 0.5 times x. That's doing the same thing, right? Because multiplying by negative 0.5 is the same thing as dividing by negative 2. All right, let's go to part D. Reformulate the statement k of 0 equals negative 1 using the inverse function k inverse of x. And this might be a little bit confusing, but just what we're doing here is like we're saying, oh, we have a mapping from x to y, which is 0 maps to negative 1, right? That's what this says. X value 0, we know that's x because we traditionally write k of x like that. So what's inside the parentheses is the number we're putting in for x, or the input. And this is the, after it goes through the function, it becomes negative 1, right? So basically we're defining 0 maps to negative 1, okay? So using the inverse function, how would we represent this? We would say the inverse function of negative 1 is 0. So do you see how it does exactly the opposite of what's here? 0 maps to negative 1. In this case, it says negative 1 maps to 0. Okay, so when you have the inverse function, what you put in here is actually the y value. Nevertheless, we write x there. Why do we do that? I would say just to confuse you, but that wasn't the reason. The reason why is x is always representing the input. And so think of it as this x here is not what you normally think of x, okay? It's not necessarily the x-axis. It's not necessarily the x in an ordered pair. What it means is this is the input. This is representing the input. So think of it as k inverse, inverse of k box, and I'm just saying, oh, by the way, it's box minus 1. Is that right? No, it's k inverse plus 1, right? Because the inverse function, we define the inverse function of k to be x plus 1, so it's box plus 1. Okay? So when you have k inverse k with x here, this isn't really an x. It's just saying input. Okay? So we know k inverse of x is equal to x plus 1. And so this mapping here, the inverse function actually always goes backwards. It always goes backwards from what we're normally used to. A regular function goes from x to y. An inverse function goes from y to x. I hope that did not further confuse you. Okay, let's move on to 4e. Remember, the idea of these videos is to generate questions and doubts in your head that you're going to go to class and ask your teachers to explain to you in more depth about the parts you might be confused about. Okay, let's look at this notation. This open circle means composite function. What does a composite function do? It's like a function inside of a function. Okay, Remember the investigation we did with the magic trick, where you took your number and did several functions on it, did several multiplications, several divisions, and at the end of it you got a number, and then I like told you what your original number was in like 2 seconds. And the way I did that was I took the 5 functions you were doing on your paper, I converted it into one simple function, and I did it in my head, and so I could put all those functions together in one function. Okay, and so that's a composite function, when you combine a bunch of functions and make one giant function or one simple function out of it. Okay, so how do we read this composite function? It's read in a way that's supposed to help you remember how to execute it. It's read as K follows J. Okay, so what do they mean by that? That means that J comes first and K comes second. Okay, if you're good with function notation, you can write it like this, which means, oh, first J operates on 1. After that, whatever comes out of J operates on 1 is fed into K, and K operates on that. If you like the function machine notation, what's happening here is that 1 gets fed into J first, and then the result of that gets fed into K, and then the output of that is the output of everything. Okay, so first what we're going to do is we're going to do J operates on 1. So J operates on 1, let's look back to see what that does. We know that the J function, what it does is it multiplies by -2. So J operates on 1 is going to give me -2, because -2 times 1 is -2. And then it says I'm going to take whatever comes out of there and I'm going to operate on it with K. And the relationship K is defined to be x minus 1, or box minus 1. So it's going to be -2 minus 1, which is equal to -3. Okay? All right, now let's do J follows K. J follows K means K is going to be done first. So K operates on 1 is going to, let's see, what was K again? K is box minus 1, or x minus 1. Okay, so that means 1 minus 1. 1 minus 1 gives us 0. Then we're going to take this, what comes out of K1, K operates on 1, and we're going to operate on it with J. So it's going to be J, and then we're going to take this 0 and we're going to put it here. And so J operates on 0. Remember, J is multiplied by -2. -2 times 0 is simply 0. So this is just going to give us an answer of 0. Okay. All right, and so that's it for page 4.